Hello everyone. Today I'm going to talk about H2O. H2O has some advanced components that help you to do more sophisticated analysis. So when you open this workflow, it would ask you to upgrade your NIME and install some extra nodes. If you look at left side of my screen, you see some yellow nodes like partitioning predictors, statistics. So these are developed under H2 names. They are different from node repository that you see here. So if it's your first time opening H2, you probably don't see this yellow section here. Just play next, next, and let your NIME to install H2 for you. Okay, but how it works and what is the goal? So for some predictions and especially some of your projects that I've looked at, so on top of having very accurate prediction, is uh, better to talk about variable importance. For example, some of your research is about healthcare. In healthcare, it's really good to have high prediction in terms of if somebody can survive, which medication might be better, so on and so forth. But we also want to look at which factors are important, which factors are affecting someone's to live more. Having said that, so let's say you want to do a surgery, a very tough surgery, maybe heart transplantation, and your model can predict if somebody can live like 5 years, 10 years, or other different time slots. But it also would be very nice if it tells you maybe weight is associated to somebody's length of survival, maybe blood pressure, maybe some hormone levels in their blood. So let's say if doing exercise is an important factor, it will tell your patient that you should do regular exercises. If some hormone levels might be very correlated and or very important in somebody's length of survival, maybe you can prescribe some medicine to adjust that hormone level and help your patients to live more. So in such a cases, for some interventions, knowing the importance of some variables are really important. This is the goal. So we want to have a very easy workflow that helps us to understand the importance of variables. For today practice, I picked a very small and conventional data set, is IRIS, which is, if let me just open it for you. It's about some plant species, and we have their width, length for different parts of the plant, and we need to predict the type of species. So just for independent variables and one dependent variable. Maybe here, some variable doesn't seem as great as healthcare example that I told you. Like, but here maybe you can understand if you want to find, or maybe if you want to have a robot to pick some type of species, which factors are important, so you can train your robots more on those specific factors. Maybe you provide some more data on, let's say, uh, petal length or petal width. Okay, there is just, it's pretty much similar to previous workflows. We just have one extra node, which H2 local context. I'm not sure if you're familiar with some type of advanced programming. So this type of program is called object-oriented. So you initiate an empty object, and in each level of your project, you add some more information to that empty object. So if you're not familiar, H2 local context is a data carrier. Nothing is in it. So the data carrier from H2 context just gets to here table to H2, And also we have a table reader, which is similar to previous workflows. So you import the data. In table to H2O, this table, which is in human-friendly format, would be attached to those data carrier coming from local context. So now my empty data carrier or objects has information of those plant species. Actually, object-oriented program is a very effective and productive way of programming. So later, if you want to learn more about programming, maybe object-oriented is basically learning this type of program is very useful, and you can make advanced programming projects. So anyway, so if it's difficult for you, just assume we have a table reader and local H2O, they should be go together so you can import the data and have it in the H2O friendly format. The next is H2O partitioning. So similar to other conventional nodes, which we had for partitioning. So I just said 80% train, 20 test, and randoms is 42. Basically, for training machine learning algorithms, we have some randomness factor. It's not 100% random. There is a pseudo-random. So there is some algorithms that create pseudo-random data with a seed. If you add a seed, every time that random number would be same. So what does it mean? Your prediction all the times would be same, even for you and for other people who use your workflow. But if I just delete that random seed, every time that me or you run project, the result are basically same, but there's just very slight differences. So having or not having random seed shouldn't be a big issue. It's just for having exactly the same result in all runs of the project. So anyway, so as you see, now my workflows has two different branches because I want to see if I can improve my prediction. So one time I try gradient boosting machine learning, and second one I use random forest. For your final project, maybe add another one. So let's go to the upper branch. Here you can include or exclude your independent variables. Here I included all, and my dependent variable is a species. For prediction, first of all, we have a classification problem. So if your final project is a regression, which means your dependent variable is a continuous number, you should use different nodes. But here we want to classify the type of plant. So I use classification. So learning classification. One nice thing about here, if I right click on gradient boosting machine learner and go to, there is a section here, variable importance measures. So let's just expand that column. We have different basically numbering in terms of percentage or like proportion. You can just pick any of them, but so as you see, petal width is the most important one to basically find the type of plant specific and length of petal. These two, so as you see, petal width and petal lengths are much more important than sepal length and sepal width. Look at the like first column, second and third one. So let's say I want to train a robot to pick that plant. Maybe it's better to provide more examples on petal width and petal length. So probably if I propose some more observations that has these two variables, I have a much better robot in picking the basically the plant that I'm interested. One thing that you can do for your project, basically, if you have too many variables, let's say 20, with this variable importance table, maybe you can pick top 10 or top 5. That's okay. And later try to make a new prediction with just by limiting yourself to the most 5 important or most 10 important variables. So there are different strategies. So maybe after this prediction, which I'm showing you later. So with the first one, I can understand petal width and petal length are the most important ones. So anyway, I go back to that section again. So in classification, it's just a note for predicting your test set, which is coming from H2O partitioning. And let's look at the score. So accuracy is 90, almost 92%. Look at this column. So which is really good. So it seems extreme gradient boosting works really well. Also, more importantly, we have something new here. I have the most important variables. So let's say in the next run, I just focus on that two variables. In some cases, you can improve your project. You might have a better accuracy. In some projects, you may not. So, okay, let's open this node, and I exclude these two least importance because I know petal lengths and petal widths are the most important. Look at this funny random seed. You can select anything that you like. So what happened? Let me just review. In the first branch, I train and test, and I found that petal width and petal lengths are the most important one. In the second one, I just want to focus on that. So let's just right-click, execute. Okay, let's see what happened. Okay, so in H2O, I should rerun the workflow from scratch. Otherwise, if I change in the middle, sometimes it doesn't let me to do that. So let me go table reader. Maybe I just make a quick change. I delete and put it back. So execute up to here. In the random forest, now I exclude sepal variable, sepal length and width, because in the previous node, I understood they are not very important. So again, let me just come here, right again. Let me go back here again. So variable importance, petal widths and lengths are more important. Anyway, so let's just train and come here and execute. So here we try to improve the prediction by using a feature selection branch, which is the upper branch, and focusing on the most important variables. Let's see what happens. It may or may not improve. Look, now my accuracy is 94.6%, almost 95% accuracy. So that's a really interesting fact. So as you see, if you try to find importance of variables, it's not only good for some cases like healthcare industry, which you can suggest and provide some insights for your doctors, medical doctors. On top of that, you can use it for prediction in another algorithm. improve your prediction performance, which by here, by just including the important variables, we could boost the accuracy. Okay, so also let's look at another application of linear programming in transportation. So first we had the very basic ones. So you have some demand and supply and try to provide your demands, considering basically some policies. So now we want to get to more advanced problem, which is including the vehicles, because it's not just demand and supply. You also have some maybe trucks that take your products. So let me just. So look at this example. We have a network of supply demand, Dora, EU, and Claire. We have demand of 275, 400, and 300. We also have supply from Ocala, Orlando, and Lee's, 200, 600, and 225. So now we want to include the cost. So sending a unit from Dora to Ocala, Orlando, Lee's costs like 200, 344, and 235, and similar for all the nodes. It's a transportation problem. So we want to minimize our cost, transportation costs. So these are the number of units, unit costs. On top of that, we know that we cannot send more than 300 per truck. So this is our truck capacity. On top of that, look at demand. So if you sum up, so demand is 975, supply is more than 1,000. Having said that, so we have more supply than demand, and it makes sense to fulfill the demand. So we want to deliver it to be equal to demand or greater than equal in some cases. If it's greater than equal, it means you provide everything. And supply doesn't make sense if you send more than what you can supply. So this is another consideration that you need to have in your problem. So two sections. Some transportation costs, demand and supply. On top of that, we have transportation costs. So material costs or product costs, transportation costs, and some limitation in terms of truck capacity. Okay, so please open transportation truck excellence. So this is, it looks a little scary at first. Later, we look at it and we solve it in a much easier way. So the first one is supply and demand capacity. Look at this blue table here. It's similar to previous transportation problem, which we had supply demand. So the blue cells here, it just means the decision variables, which talking about how much you send from each supply node to demand nodes. This is capacity of the demand. We need to fulfill them. And also these are supply capacity, supply cap. So, for example, giving that Dora is a demand point, how many products you get from Ocala, Orlando, and Leeds. Summation of these points which is each of these three means how many units from to send, how many units you send from those three nodes to your demand node is here. So summation of H12 to J12, this blue section, it should be at least 275. You want to fulfill the demand. In some cases, you might have different policies, less or equal, greater equal. So it's just is just based on your type of policy. Do you want to fulfill all the demands, or is it okay you might have something less than demand, or maybe exactly equal to the demand? Each column is talking about how many products you send from each supply node. For example, Ocala, how many you send to Dora, EU, Claire. And this point has summation of all of them. So these blue cells, it just means each of them means how much Ocala sends product to Dora, EU, and Claire. Same for Orlando and same for Leeds. The zeros here, these cells are zero here because it's just formula of summation of all supplies that you sent from Ocala. And we know supply shouldn't be the more than capacity of Ocala. Same for Orlando and Leeds. So first blue table is first decision variables, talking about how you want to follow your policy in terms of demand and supply. And also we know something should make sense. So you shouldn't send more than what you can supply. Okay, so besides, I have a decision variable about my transportation, which truck I want to send from each supply nodes to demand nodes. For example, if Ocala has just 200 units, doesn't make sense to send one truck to Ocala and one to Clare. Right? Because the truck has considered 300, why I just put 100 on each truck and send to two different nodes? I would increase my transportation cost. Doesn't make sense. If it's like my supply is 600 in Orlando, two trucks is very efficient, 300 on each, because this is my capacity. Maybe 3 Dora or AU. I don't need to make 3 trucks, which on each I should put 200. So 200 times 3 would be 600. If I send 200 in each truck, I'm not fully utilize the truck capacity, which is 300. So the second blue table is second type of decision variables, which you want to decide which transportation plan you have. So if it's one in each blue, it just means you use one truck in that origin destination route. Okay, so far we talked about two decision variables. First decision variable is just saying which how your demand and supply nodes would be work. So how many products you send from one node to one supply node to the another demand node. On top of that, how you send your trucks. So second bullet table, just maybe considering your policies, you want to send one or more trucks on each nodes. Okay. We also talk about demand constraint and supply constraint. In this problem, our policies we fulfill all the demands, sending at least equal to 75, 400, and 300, and we shouldn't send more than supply. It doesn't make sense. Second type of constraints is about your truck capacity. So do you remember we talked about 300, the capacity of truck? We already decided a decision in second bullet table about how many trucks we want to send. So let's say here I decide to send one truck to Orlando, one truck to Clay. So the truck plan shouldn't be 400 and 200 here. So 400 to the Dora and Claire. First of all, demand capacity constraint, but on top of that, here I'm sending 600, but my capacity is 300 units. So I cannot use it. I cannot just use one truck here, maybe two trucks. So anyway, at the end, you should consider that these supply demand decisions should follow your truck capacity. And we have a plan. So if I send one truck here, my Orlando to Dora shouldn't be 400. So for making it easier, I make another table, which is about truck capacity. Is nothing just my transportation plan times truck capacity. So all these yellows are just formula. Number of trucks that you decided in the second decision table times capacity. And I would make a constraint here connecting this yellow table to first blue table. And all the things that I have in the blue cells should be less or equal yellow cells. Because it's just saying how much capacity I can have on that, or how much product I can sell in that cell. Okay, so two decision variables about quantity of products, about how many trucks, two types of decision variables, one following demand capacity, demand policy, supply policy, and the last one is truck capacity. So this yellow cell would be number of trucks that you make in the second blue cell times 300, showing the capacity of that link, which, like for example, Orlando to Dora link. So whatever capacity of truck you have here should be more than products that you send in that link. Okay, let's open the solver. Okay, by the way, I forgot to talk about objective function. The objective function is minimization. So we have two types of cost. First, good cost. So whatever you decide in the first blue table is the amount of products or goods that you can sell in that link times the unit cost. Okay, so unit cost times how many you send gives you the cost of goods, this yellow cell. The second cost is just transportation cost. So whatever you decide in the second table as a second type of decision variables times truck unit cost, which we have the coefficients in this top right table. If you, for example, if Orlando Dora is send two trucks, 2 times 344, your cost will be 688. So total cost just is summation of these two, summation of goods cost and truck cost. So if you open the solver, you can see I'm trying to minimize my C12, which is total cost, summation of goods and trucks. Look at the first unit, H12 to J12, H12, first blue cell, last cell on the first table, is less or equal N23P25. N23 P25, which makes sense. These are just capacity of each link, for example, Ocala to Dora or Orlando to Claire. So the yellow cell, which is N23 to P25, these are capacity of the link. So first blue table shouldn't be, all the cells in the first blue table, which is amount of goods, should be less than yellow cells, which is capacity. Okay, second constraint is H16 here to J16 less or equal H17, J17, which makes sense. This zero is basically just formula of summation of columns. And summation of columns means how much you send from each column name, which is the supply node, to other nodes. So whatever you send from Ocala to other nodes would be sum up in this zero, which is like formula summation, should be less than Ocala supply cap, and same for others. Okay, so let's look at the last one, K12 to K14. So demand greater or equal L12 to L14. Maybe here you might say why you shouldn't make exact this, equal. That's okay too. So if I don't specify any policies, you are flexible. But here just means we want to at least provide the demand. Maybe in future we have more demand, we don't know, or we are not certain. So maybe it's okay to send some more products there. But we are sure, we should fulfill all the demands. And the third one just saying that H12 to J25, H12 to J25, H23 to J25, just saying the trucks are integer. We don't have any like half a truck. So all the trucks are integer. Simplex is the method. If you solve it and press, you can answer. But the answer is here. So looking at binding and not binding constraint. So from Dora to Ocala is 200. Oh, let me see. The answers didn't show up. So H12 and 23. Oh. Okay, it seems in Orlando, it didn't touch the constant, basically supply capacity, which makes sense. You produce too much in that point. So anyway, it's the way that you learn linear programming. You need to expose yourself to more and more problems. Pretty sure in the future, if you make this problem a little more complex, you can understand how it's going on. So, by the way, but you shouldn't be worried. It's the way that you learn linear programming is kind of different from other courses. It's not that much of reading. It's just you need to expose yourself more and more. I'm going to post a homework later today, and on Tuesday, and you have 1 week. So I hope it could be. I will hope that it could be easy for you. But otherwise, you can help your friends over grouping and share your experiences. So hopefully, you would get a really good grade in that. Anyway, thank you very much, and have a great rest of the day.